So, hello again. Welcome back. Hopefully, you all are okay from the hurricanes and things. Crazy start to a crazy semester already. So, today we're going to talk about units and mass balance. Last time we just kind of gave an intro to the class. This is some more introductory material. Some of this is going to start getting to chemistry, although we'll focus more on that next time. It might seem basic and boring, but I wanted to give a nice, thorough basis for you to begin thinking about our mass balances, kind of the way we compare anything in our class. You know, we apply some treatment to a system. Well, how are we measuring the effectiveness? Okay, so I wanted to make sure that you have the background here, have the resources to understand what's going on a kind of physical, like what's actually happening level. So that's why I'm starting them saying units are essential. Okay, units, even if you forget how to do a problem, if you go through and look at the units, and if anything, memorize what the units are supposed to be from the formula tables, from the equations that you have. If you know the units for each parameter, chances are you're going to be able to discern and figure out how to do the problem, even if you completely forgot the process. So, as with probably most all of your classes, units are really essential. We're gonna keep in mind that conservation of mass is assumed, and so those two principles here, we're gonna be able to solve basically all the problems. So when we talk about mass balances, and I'll elaborate on this after we cover the units, really what we're talking about is the change of some mass or some number of things over time. And that's what we call a rate. So we're gonna deal with rate constants, things like that. Really what we're looking at is the rate of change. And we compare how much is accumulating in a system, and we can set that equal to how much is being added to the system versus subtracted versus what's happening with any reactions in the system. So we'll take a look at that, but basically we count up all the different ways that the mass or the number may be changing, and we do our analysis in that manner. Okay, so chemistry then, when we talk about chemistry, we want to be able to do these rate analysis, these mass balances with chemicals involved because we have to use chemicals for water treatment, right? It's fairly obvious we have to deal with some chemistry. Okay, the chemistry I'm going to remind you of, about 90% of that's going to be all just units, okay? And chemistry, from my experience and a little bit of experience teaching and even learning it, what I realize is getting the units right is the biggest challenge, because we jump into moles and molar units and all that, and you add in some other chemical concepts, and you get lost pretty easily. So again, I'm just going to come back to the basics and remind you that almost all of what we're going to deal with here is just units. Okay, so once you get the units right, you'll get most of the chemistry right. All right, so concentrations going to be the basis of most of our chemical analyses. We're going to do, maybe a mass balance on a concentration, so mass per volume or number per volume, not just the mass, but when you're comparing concentrations, it's like 5 milligrams per liter compared to 10 milligrams per liter. That per liter, it's going to help you. It's kind of going to drop out of the equation. So we're still dealing with mass or number, but kind of on a volume basis when we're dealing with concentration. All right. Okay. So SI conversions in line with units. You've seen this before. I expect you to be able to know, what's a kiloliter. If I were to give you that unit, it's 1,000 liters, that type of thing. So be familiar with chemistry. Sometimes we will go down even to nanomolar, something like that. So be familiar with what that means. Chances are, most of the time we'll just be dealing with micro. So micro and milli. Those will be the common ones, but I do expect you to know that nano is times 10 to the minus 9th, right? So pretty straightforward there. I'm going to talk a little bit more about some other SI conversions I expect you to know that you might not remember. And one note here, when we're talking about units, look at the, this is the equation table, the formula table, or the reference table I'm giving you on the exam. So this is already on Moodle. If you look at the dynamic viscosity, again, highlighting the importance of units, this number here is built into the unit. So when you're taking your exam and you're checking the units, don't make the mistake of just taking the number straight. So you'll be given a problem and it says, okay, 15 degrees Celsius. You go over, okay, you needed this number and this number. But when you're checking the units, make sure that you're recognizing that you have times 10 to the minus 3 built in here in that table. Okay, so definitely pay attention to that. It's a little tricky, I know, but this is the table, and just be warned. Okay, so a few units I'd like you to be particularly familiar with would be volume conversions from length cubed to liters. Okay, and there's actually some shortcuts here can help you remember in case you forgot. So probably the easiest thing to do would be to commit to memory that there are 1,000 liters in 1 cubic meter. Okay, if you're going to memorize something, that's probably the easiest way to go. You could also take a look and if you did the math, you'll notice 1 milliliter is the same as 1 cubic centimeter. Now, that gets a little bit confusing because, you know, if we just look back up here, you'd think, okay, if it's, you know, meters to centimeters, that goes down to 1/100th, whereas liters to milliliters is 1/1000th. And that's just because you're cubing, when you cube the length, you have to do that conversion multiple times. So it's that's why it works out differently. So as a quick challenge, and a kind of a way to challenge, like to consider how to go about this, answer this question. Okay, how many grams are there in 1 milliliter of water at 5 degrees Celsius? So this will just be kind of a quick little practice, making sure you're comfortable with it. I'm going to come back up to the table here, the density table. And so we're at 5 degrees Celsius. We've got the density here, and we've actually defined the density of water and all these to be exactly 1,000 kilograms per cubic meter. So, sorry. So we'll say rho is 1,000 kilograms per cubic meter. So give that a second. so hopefully you've had a moment to think on this. The answer here is actually something that you could also commit to memory if you wanted to. It turns out that this is another kind of standard or straightforward answer here that you could commit to memory, and then you can use this table, and then you could always convert if you ever forgot the 1,000 liters in 1 cubic meter. Okay, so if we take this, we say, all right, let's get this into grams. We can just multiply, get my cursor, there we go. If we multiply that, we know there's 1,000 grams in 1 kilogram. So we multiply that. Then we can also convert from cubic meters to milliliters. So to do that, we'll take what we know, this 1 cubic meter per 1,000 liters, multiply that in, and then we also have, again, to convert from liters to milliliters, 1 liter per 1,000 milliliters. Okay, so with that, if you multiply all those across, we should get our kilograms to cancel with the original units. The meters cubed should cancel here, and then we're going to take those liters from into milliliters, and those should cancel as well. So if we do all this, we should end up with 1 gram per milliliter. Okay, so fairly easy to remember, and if you've ever worked in a lab, done anything with a pipetter, or even if you had like a medical pipetter or something at home, you see like the 5 milliliter mark or something, or have some grasp of how much 1 milliliter is. We actually calibrate pipetters, those little volume things, based on the mass of water. So if you know the temperature, you can get the exact density, and then you know exactly how much volume you're pipetting based on the mass observed with that. So that's actually one way we calibrate those. Okay. So that's just one quick example. If you are finding any trouble with that, just go back, take a look at the units, make sure you're comfortable with that sort of process. We have to do that all over the place, and I'm going to expect you to be able to do this when you encounter problems that we haven't covered specifically, but having this process. Okay, so this type of analysis, or this type of process, is really helpful when we get to molar concentrations. We'll talk more about it in a couple minutes, but really going from a number to a mass is the critical component of molar units. If 10 atoms of hydrogen react with a specific number of some other atom, that's a number comparison. If we're doing a reaction, we're often comparing the number of atoms and molecules. It doesn't matter their mass, because it matters what type they are and how many there are to react with each other. So we have to deal with numbers. It's like, if you wanted to know the mass of a dozen eggs, you need to know the mass of 1 egg, right? So then if you know that, you multiply by 12, so that's a dozen, and then you can have the mass of a dozen eggs. We're going to do that same thing with the chemistry, and sometimes you need to be able to do that type of conversion. Okay, so before we get there, I'm going to talk about concentrations, and really what we're dealing with concentrations is my technical definition here, the amount of stuff in an amount of other stuff. Okay, so super technical here. Basically, we have some volume, and let's say it's filled with a liquid with some sort of solute or particle in it. What we're counting is the number or the mass of that stuff that's in it per volume of the water, the liquid, whatever we have. Could draw this like a beaker, and you have stuff in it. Maybe it's cloudy water, and you want to count how many particles of sand there is in there, or silt. Whatever the case is, what we're looking at is that concentration, how much of that particular stuff, if you were to separate it completely, what mass of that per volume that's containing it. So we want to take a look and describe, all right, what are the different denominators we could use? So if we wrote this as stuff maybe in a liquid. Now you can do this in air as well. Sorry for the handwriting. I have my screen on here that I'm reading to try to write is like this big. So it's not the easiest. I might be able to make it bigger for myself. Work on that later. Okay. So if we do that, then there's a couple different denominators we could look at. We could have a volume basis. So the volume, maybe in a bucket, you have 5 gallons. Maybe it's 20 liters, something like that. What's the volume basis? That would be liters. You could do cubic meters. You can express this as a percentage. You've seen this if you look at alcohol or cleaning solutions, things like that. You'll have percent by volume sometimes. So that's what percent of the volume consists of ethanol in the case of maybe some sort of alcoholic beverage. Instead of volume, you could do mass. So sometimes you'll see things that say grams per gram or milligrams per kilogram. A lot of medical things will deal with how many milligrams or even nanograms of some substance can a human or animal handle per kilogram of a body weight. So a lot of times the dosage of some medicine will be determined based on your weight, because we know that the impact can be best described in terms of milligrams per kilogram. So that's one way you might see it. You could also do that by percent by weight. Okay, so the same thing as the percent by volume, but you're doing it. Okay, you add 1 gram of something into a liter. Well, what is the what percent of that stuff that you added, that 1 gram, is it in terms of the whole weight of the solution, right? You could do that percent by weight. Okay, given that, there's a few different ways we can describe this in kind of shorthand, and we do this very often. So percentage you're all familiar with. We've heard that all the time. But we can also call it parts per X, parts per thousand, parts per million, parts per billion, even parts per trillion. So these metrics are essentially just percentage. So when we take a look at parts per thousand, really, and there's actually even a shorthand, you can write that as this little percentage symbol with an extra 0 on the bottom. What we're saying is, this is, if we say 1%, then 1 part in 100 is X. So 1% X means 1 part in the 100 is X. If you do parts per thousand, then 1 part in 1,000. Okay, so it's really the same principle, and we can do that percent by weight, percent by volume. So we could also do parts per million by weight or volume. Usually we're going to do, it's pretty common to do mass. It's pretty common to do mass, especially in chemistry type stuff, because we can assume that for the volume, it's going to be liquid. It's going to be liquid with a density of about 1,000 grams per liter. So 1 kilogram per liter. Yeah.
What's that percent sign?
This percent sign means parts per thousand. So if our normal percent sign means parts per 100, so this is then this guy is parts per thousand. Now, I don't usually use that in writing. I just wanted to kind of show you and help you relate that concept here. I guess maybe you could write one that's got 3 extra zeros for parts per million, but I've never seen anybody do that. Okay, so it's the same concept. So if you see that, just remember you can equate it to a percentage, just having a bigger denominator there. All right. Okay, so talking about concentrations, I wanted to add a little bit of context as we introduce chemistry, which is why I have a GIF here. So talking about the numerators, what's on top, we can use mass or number. So mass, it would be like milligrams per liter of OCl minus. Or you could have number, maybe the number of particles or the number of bacteria per liter, per whatever, per volume. And when we deal with chemistry in the molar units, really what we're dealing with is the number, a number volume or a number concentration. So a mole is really just almost the same as saying a dozen, okay? But instead of 12, we have this massive number. Okay, so in chemistry, we get a little bit more context here, but 1 mole of X is 6.02 times 10 to the 23rd of X. 1 dozen of X is 1.2 times 10 to the 1 of X. Okay, if you see what I did there, this is just 12, right? It just looks fancy, sounds scientific, and could scare you. But literally, it's the same thing. So what I'm trying to emphasize here is this concept of moles, which maybe you'd run into in high school and stuff, and haven't bothered with it since, and you just remember it was annoying and confusing. Well, it's a dozen, just with a bigger number. So the question is, how many eggs does it take to properly egg a car? If you think about that, are you going to compare it on a mass basis? Okay, well, 1 car maybe weighs 1 ton. Do you need a ton of eggs? 1 ton? No, that's going to be way too many, right? That's going to be an absurd number of eggs. If you're trying to be very thorough here, like this little dude, maybe 1 for every window and 1 for every door handle. I don't know, but that's going to be maybe a dozen, right? So if you think about the appropriate amount, you don't compare that on a mass basis. And I'm making it absurd, so hopefully it kind of sticks with you a little better, like eggs. All right, so given that, we're not going to, if we did have to calculate the mass of eggs, then we need that conversion from, okay, how much does 1 egg weigh when we know it's going to take 20 eggs, right? Or instead of 20, maybe I'll say 1.5 moles of eggs, except not moles, let's use dozen. 1.5 dozen eggs, okay? We need that conversion of how much does 1 egg weigh. Okay, so that's the whole principle of our chemical conversions here when we deal with molar units. So if we take a look at the periodic table, you'll see all the elements like this, and we have this atomic, the atomic number up top. That's just how many protons it has. That's the, you could order them all 1, 2, 3, 4 up to however many we know about right now. This atomic mass here, this is what tells us how much each one weighs. Okay, and there's some nuance here. The decimal places are really describing the average we know about on Earth, given that there's some isotopes. Some have some neutrons and some don't. Don't worry about that. It's not really going to affect much. You just feel free to use these. Usually it won't make too much sense to go out past a couple digits. And sometimes you'll see me shorthand hydrogen, for example, to 1. And that's okay. All right, so what does this mean? Well, if we have moles giving us kind of a number basis like a dozen gives us, then 1 mole of hydrogen here is 6.02 times 10 to the 23rd hydrogen atoms. Okay, then this atomic weight this number here that I highlighted, this is what we call atomic mass units. So there's so AMUs, this is called. You don't really need to keep this in mind, but literally what this means is one hydrogen weighs approximately one atomic mass unit. And that's actually how we define it, right? One proton is one AMU. One neutron is one AMU. Okay, so given that, we needed some convenient way to convert from this mass of just one of them to something we could tangibly grasp as a concept. So what we did was we said, all right, how many of these atomic mass units yields 1 gram? Because 1 gram is kind of convenient. You know, we can weigh that out. Maybe this pen cap might be a few grams, something like that. Not exactly sure, but it's probably on the order of grams, maybe tens of grams. So that's tangible enough. And so what we decided was, okay, we're going to use this Avogadro's number, this mole, like a dozen, and say, all right, how many does it take to get 1 gram? So convert 1 AMU to 1 gram. That turns out to be this 6.02 times 10 to the 23rd number. Really just designed there to shorthand for us. Okay, so we don't even really probably need to know this number for the class. I usually don't even ask you problems that need it. So long as you know that 1 mole of hydrogen is going to weigh this many grams, right? So 1 mole hydrogen is equal to 1.000794 grams of hydrogen. That means we can say that we, on a number basis, we know or can describe relatively easily the molar concentration of things without dealing with this massive number. Okay, it's really just a shortcut, right? Dozen is just 12. That's not, that doesn't do a huge thing. But for eggs, 1 dozen, 2 dozen, that at least puts it in a place where we're familiar with how we use that. Okay, this is a much bigger shortcut in that that's a much bigger number. Okay, so then we do molar concentrations, moles per liter. Whenever you see a capital M, so if I say something like 4.3 capital M of H plus, you can assume moles per liter. Okay, the capital M is always going to mean moles per liter. The other thing that's always going to mean we're dealing with moles per liter are brackets around our concentration here. So if you see brackets with this nitrate here, I'll erase them for now. Those brackets are telling us we're dealing with moles per liter concentration. So if I give you that bracket H plus equals 3.6 times 10 to the minus 4, you can assume that that's going to be moles per liter, okay? And you should. Every time you see those brackets, it will be moles per liter. So if I just write it out like this, or you see this in a problem or something, just go ahead internally, remind yourself that this is moles per liter, okay? So hopefully that'll save you some headache when we're dealing with some of the chemistry. It's easy to accidentally use a mass concentration. If I give you, in terms of water treatment, oftentimes there'll be some operator that needs to know what mass of this stuff to pour into the tank, right? And have to operate on that basis. We often cost things based on mass. We often, we're often dealing with mass units. So when we have a problem, sometimes you'll have a mass dosing for chlorine, let's say. Now, the important thing here is to convert from mass to moles so that we understand what's happening on a numbers basis, because we have to. Then we come back to mass, and sometimes, yeah.
So is a mole like a weight, or is it just amount of something?
No, the mole is an amount. Okay, you only can get the weight from having that atomic weight.
So each atom has
Yeah, so every atom is going to have its unique atomic weight, and every molecule is going to be just, you add those different atomic weights up, right? So H2, fairly obviously will just be 2 times that number. And we'll say this is approximately 2 here.
And how many moles would that be?
So whenever we're writing a chemical equation, what we're going to do, and that's an excellent question, what we'll do is we'll write, it'll look something like this. And I've got a question on chat. I'll get to that in just a moment as well. So let's say we have this equation, 2H2 plus 2 oxygen is getting us 2H2O. Okay, so what we're dealing with here is the 2 in front of the molecule. This is the number of moles in the equation. Then this 2 is the number of atoms in the molecule. So in total, we have the 2 times 2 atoms. So that's 4. If we said we had exactly 2 moles of hydrogen, H2, then we have 4 moles of hydrogen atoms, right? Because the molecule contains 2 atoms, and we have 2 moles of that molecule, so we have to multiply it by 2. Does that make sense?
So, like 2 moles of that. So it's 2 moles of that molecule.
Yes. So the number out here, this is the number of moles of that
So it's
molecule.
Not really like a set amount.
What's that?
It's never really a set amount. You just kind of define it. How much of the amount you want.
Usually when we're drawing up an equation like this, we're doing some sort of ratio.
Yeah.
So if we're forming water by oxidizing hydrogen here, this isn't maybe the best way to express it, but if we're doing this, then we know that we need 2 moles of oxygen atoms per 2 moles of hydrogen, in this case, hydrogen H2. So in that way, we could actually probably be more correct if we were doing this in the normal conditions. This would be 1 mole of oxygen gas, right? That would be actually how we'd normally see it. So in this case, we have 2 moles of hydrogen gas plus 1 mole of oxygen gas is going to give us 2 moles of water. So it is a little bit arbitrary. We could say 4, 2, and 4.
Yeah.
That's fine. But we're matching up that number to number ratio. And this is why we have to deal with moles, is because this could be atoms. We don't have to say these are moles here, but for our example, so that we can work in grams, it's a lot easier, right? So if we know the atomic weight here of hydrogen gas is 2, it's very easy for us to see, okay, we need, let's say 4 grams of hydrogen atoms to do this. So it'll be a little more clear as we go through more examples. Did that answer your question?
Yeah, but it's okay. I'll just keep going.
Okay. And I've got another question here. Okay. Somebody's asking, so it's like a measuring cup, it'll always be that value depending on the item you're measuring, could be heavier or lighter. And that was in response to something I was saying earlier. I think that sounds correct. Yeah, so essentially, if you take a measuring cup and you fill it with different types of atoms or molecules, it will weigh different amounts. Even if you have the same number of moles in that cup, it'll weigh different amounts just because the atomic weights differ. So let me know in the chat if that answered your question. Okay. Thank you for the questions. Please continue asking. I'll do my best to clarify, and I might make another blank page just to write out some more notes in a minute. Okay, so another way we're going to use number concentrations will be for disinfection, and for any time we're dealing with particles in water, we don't well, sometimes we'll weigh them, but a lot of times it'll make more sense if we're looking at the dynamics of particles sticking together in what we call coagulation, that kind of process, it'll make some more sense to actually identify on a number basis how many particles we have. With regards to disinfection, you've probably seen fairly often, such and such kills 99.9% of germs, or just 99% of germs. Now, you may think at first, okay, researchers, to define this, the company or researchers or whoever, took 100 different types of germs and it killed 99 of them. That's not actually what they're saying. That's not actually what it means typically. That might be true. Usually what it means is they took one specific germ, let's say E. coli, for example, and then they subjected it to the treatment, and 99% of them were destroyed given whatever time and dose they provided. So that 99%, really what they're talking about is a comparison of the number n. We're going to use n for the number for most of the class. So the number n, that concentration of germs per volume, and this is going to usually be in colony-forming units for bacteria. That's how we count them pretty often, or plaque-forming units, that's for viruses. You'll see that fairly often. So this would be bacteria. That's just a function of the way we can count them in the lab, or viruses here. Okay, and again, what we're often doing is enacting some sort of treatment, and we're looking at how many were there before versus after that treatment. So we need to know the initial concentration N naught and compare that to the final concentration N after the treatment. Okay, so in the case of 99%, we could imagine that as N equals 1, N naught equals 100. So then if we were to take a look at N over N naught, that would be 1 over 100. And that is, and I think I have this written up on the next slide, that is basically the fraction that survived, that made it through. This is 0.01. You can write that as the fraction survived. And we could also take that and multiply it by 100%. That would be 1% survived. Okay, so pretty straightforward. We'll see this a lot with 99% removed, something like that. And what I want you to be able to do is convert that back into this fraction so that you can calculate the n, if you know the n naught, for example, and you know the fraction, right? So you're going to have to be able to work with problems where you solve maybe for one or the other, or maybe you're even solving for the ratio itself. Okay, so this is going to be, you'll see this a few times, and it'll be good for you to be able to be comfortable with that type of conversion. And as we'll see in a moment, 1 minus, so we just looked at n over n naught, that's the fraction remaining. 1 minus that is the fraction removed. So if we were to take, again, like I was just drawing, if we were to take this 1 over 100, that's n over n naught. And then we were to take that and say, all right, so that's 1% remaining, or the fraction remaining. Well, if we do 1 minus 0.01, that's going to give us 0.99, right? And then we can multiply that by 100%, and that gives us 99%, and this is removed. Okay, so if I give you a problem that says how much chlorine do we need to add so that we can achieve 99.99% removal. Okay, that tells you, if you kind of take that backwards, okay, you're looking at the removal, you're given this design criteria, and then, okay, we probably need to convert it from that percentage into a fraction. You'd have 0.9999 in that case. Okay, well, to get to the fraction remaining, you would need to solve for, okay, 1 minus what equals 0.9999. So you'd get 0.0001. All right, then from there you can recognize, okay, n over n naught is 1 over 10,000. Or you could just, there's different ways of shortcutting that process, but being familiar with navigating through here is going to be very important. Okay. So another way we discuss this type of number, the percentages, especially when we get to the 99.99, all that, we often use what we call log changes. This is just logarithm scale, and we often will say, okay, how much does it take to make a 3 log reduction, for example. So log reduction, that's a common way that we'll talk about it. And in this case, a 3 log reduction of bacteria or whatever, we would say that's equivalent to log of n over n naught. So if we take the logarithm of that n over n naught, and in this case, if it's a 3 log reduction, we define it as log over n over n naught is equal to -3. So that's where the 3 comes in. And really what we're talking about, so a 3 log reduction is 99.9% removed, okay? And really what we're talking about is this 10 to the minus 3, that 3 here is our 3 log reduction, okay? It's just shorthand. You could also imagine it as moving the decimal place 3 times, so 3 nines behind so for the fraction removed, that's 3 nines, and then your decimal, that's your fraction. So whatever way you like to think about it, again, it's just a system. I'll give you a problem saying, okay, we need a 4 log reduction. What I'm looking for you to do is just have this as part of your working vocabulary, understand what that means if you see it on a problem. Okay, so moving on from there, again, feel free questions at any time, I'm happy to answer. So I'd like to get into mass balances. So in terms of mass balances, really what we're looking at, as I mentioned earlier, is an accumulation rate. So if we imagine a system, and typically we'll draw a circle or some sort of a bounded area to be our control volume. You'll see this in the book. It'll talk about it that way. Now, our control volume is really the area in which, or the space in which we're looking at accumulation. And the accumulation rate is going to be kind of the fundamental thing that we're looking at in basically all of our problems. This could be accumulation of mass or number, and it's pretty much always going to be over time. So often we can assume it's mass per time, or we can look at number per time. Okay, so the time is what makes it a rate. And so in our equations, we're always going to have units one or the other of these. Okay, so again, coming back to our units analysis, whenever we look at different components that relate to the mass balance, the net units should be mass or number per time. Now, I'll say that I'm saying mass or number. We can also use concentrations, right? Because this is the same thing as saying the mass concentration or number concentration per time. So mass, I'm just going to write it up. Number mass, number, or mass or number concentration. Okay, any of those per time. That's our base units for an accumulation rate, or any of our rates. Most often we're going to actually be dealing with concentrations because we're dealing with water. Okay, given that, we're going to have an input rate, an output rate, and we may have a growth or decay reaction. Now, we don't have to have each one of these components. So when we talk about a mass balance system, we might have no reaction. Maybe we're just mixing two chemicals, two streams coming in. We don't have to have just one input. In fact, the very simple problem we're going to look at next is going to be two streams coming together mixing, one stream going out, doing a mass balance at that spot where that happens. So in our problems, we'll look at, okay, is there a reaction? What direction is it? Do we have an input? Do we have output? And really, we're just going to be looking at the amount of mass or whatever is accumulating within this circle over time, given those features of the system. A lot of times we'll deal with systems that have an accumulation rate of 0. We actually design a lot of our systems this way so that we can know that, maybe we are removing some contamination from our water. Maybe this is a wastewater treatment. We're removing maybe some fats that are coming into the water from maybe a cooking facility. So what we don't really want is to have more and more fats accumulating in here. We also, if we have a steady stream of them coming in, we don't really want, it's not really reasonable to design it so that we have less and less and less over time. What makes more sense is in this reactor, inside this little portion, we are getting rid of it, but it's getting rid of it at a constant rate. We have it coming in at a constant rate, we are getting rid of it at a constant rate, and it's leaving at a constant rate, whatever is remaining. So a lot of times what will happen is we just want it to stay constant so we know exactly what's coming in and going out, right? So the point here, even if we do have a reaction, is typically we'll operate in steady state. This doesn't always happen. We'll look at a couple examples that are not steady state. If it is steady state, this accumulation is 0, and that makes our mass balance equation a little bit simpler. So all of our mass balance equations are going to look like this at a fundamental level. So we have an accumulation rate that's going to be equal to the input rate, so what's coming into the system, minus what's going out, plus anything that's growing, minus anything that's decaying, so any reaction that's causing decay or growth. Okay, given all of that, this system, we can model any system with this. We're just going to have to add different pieces. We'll look at, so particles for particle separation. One thing that we'll have is a decay rate where particles are sticking together. That rate equation, the rate constant there, is going to depend on several different factors about the particles. Maybe their size, the viscosity of the water, stuff like that, how likely they are to collide. So we're going to go through the class, we're going to take a look at growth and decay rates in different systems. They're all going to use this basic mass balance equation, but have different ways of finding the rates, specifically the growth and the decay. We'll pretty much always have similar input and output rates. Again, this is just going to be some input or output rate that's kind of a concentration per time. Most often we're going to have, in terms of one of these rates, especially the input and output, there's going to be some flow rate, Q, multiplied by some concentration. Let's say C for concentration. And if we multiply a flow rate times the concentration, that's a volume per time for the flow rate times mass per volume, and we end up with mass per time, right? So our mass accumulation rate. Okay, so in almost all these systems, we're going to have something like that, where the net is mass per time. All right, so let's do an example problem. We have in our book, page 8, 1.4, we're given that we have a stream flowing at 10 cubic meters per second, has a tributary feeding into it with a flow of 5 cubic meters per second. The stream's concentration of chloride upstream of the junction is 20 milligrams per liter. The tributary chloride concentration is 40 milligrams per liter. And we're going to treat chloride as a conservative substance, meaning there's no reaction. So chloride, by the way, this is just simply Cl minus. This is different than our active chlorine that disinfects stuff. This is just like table salt type chloride, sodium chloride. This stuff doesn't really react very much, and it's just in the system. Sometimes we can use it as an indicator of pollution. Okay, so treating chloride as a conservative substance, that means when it says that, it's giving us the info here that we have no reaction. So that means no reaction, and we're assuming complete mixing. We're pretty much always going to do that unless it's a specific case where we say otherwise. Complete mixing of the two streams, find the downstream chloride concentration. So we have this control volume that's drawn. We have the concentrations labeled here. So basically we have the system, two streams joining. What we want to know is the flow and the concentration going out. Okay, so I'm going to give you a little bit of time to work on this. All of the information is actually in this picture, now that we understand that there's no reaction or anything. So I'm going to just give you the picture here, remind you that our accumulation that's going to be the input minus output. And I'm going to say plus 0 because we have no reaction. All right, so take a minute, work on that.
I just want to be clear. We were assuming steady state for this, right?
So it's a good question. And if you think about the problem, we've got two streams and we were told that they just have this amount coming in. And when they come into mix, there's no reaction. So you can end up assuming steady state because you can assume that they would have told us if the amount coming in was going to change. And since there's no reaction, there's no way it could be anything different, right? Given conservation of mass, if we have the same amount coming in the whole time, then yep, we then assume, oops, sorry. Well, I didn't want to end it, but there we go.
So are you saying that whenever it's a conservative substance, it will be steady state, at least for the purposes of this course? Or?
That's fair as long as the source remains constant.
Yeah.
Yeah. So
when it's a conservative substance, it's basically like something we'd have done in fluids at that point.
pretty much. So I would say that unless somehow you're changing the amount that's coming in, maybe a flow that's reducing or a concentration that's reducing over time, you could have a different input rate like that, but otherwise, yeah. So most of the course we will assume steady state. There'll be a couple problems here and there, and it makes when we get there, it'll make the derivation of the rate equations a little bit different. But what I'm hoping to do with you guys is help you to be able to get there on this mass balance level, regardless of what the reactor actually looks like or what's actually happening. Okay. So we take it as steady state here. Okay, good. So if we do that, we know that 0 equals in minus out, and that again it should end up looking obvious once we really take a look here, because the system is actually fairly simple. So we have 0 equals what's coming in minus what's going out. So we could also write this as what's coming in is equal to what's going out. And of course, what I mean is input rates, output rates. And this is going to be true for conservation of mass. Okay, so then what we can then write this as is we can say that our well, let's reverse this. Let's say out is equal to in. So what's going out is this Cm times Qm. If we do that, again, this is a concentration mass per volume times a volume per time. So we're getting mass per time here. So that checks out. That's going to be our exit rate, our output rate. And then we can set this equal to the combination of these two. So we have Cs times Qs plus Cw times Qw. Okay, so that's just basically showing us that we have, if you look at each one of these terms, this is going to be, you can look at them in units and say, okay, mass per volume, volume per time. Volumes cancel, mass per time. Great. And that's true for each side. And it's going to be very common for us to do the concentration times flow rate for almost every one of these systems where we have stuff flowing out. We're gonna use that. Okay, from there, well, we have two unknowns here, so let's think about what to do with that. We do know that the flow rate should also be conserved in terms of, we're not compressing our fluid. We know that water is rather incompressible, and it's certainly not expecting anything to change there with open stream. So we're going to say that Qs plus Qw should be equal to QM. So we can go ahead and solve for that portion because we weren't given anything to indicate otherwise. You know, we're not losing water to the groundwater, something like that. We weren't told about evaporation, things that could affect it. So fair enough to assume this here, and so then we could say QM should equal, what is it, 10 plus 5, 15 cubic meters per second. It's actually quite a lot of water. Okay, from there, we can solve for the CM, because then it's going to be simply CM equals this CS QS plus CW QW, all that divided by that 15 cubic meters per second. Okay, so really, you could actually think about this. You could do pretty much the same thing even without a flow rate. If you were just looking at this, adding volumes together, it's really the same math as, you know, if you're in the lab and you're mixing 2 beakers of water, each have a certain amount, and you want to know the final concentration, add up the total volume at the end, is actually the same exact math. So at the end of the day, it does you do realize this is very trivial, but what we did was we walked through it in this accumulation rate, input, output. So that's what I want to do for you. And as we add pieces, it becomes less trivial and less intuitive. So I'm hoping to connect those two to help you recognize this system, this process of doing it, to connect those dots. Okay, so if we put in the numbers, we have all of these numbers now. So if we were to do that, the answer should be 26.7 milligrams per liter. All right. So any questions on that? Yeah.
How did you know to just cancel out the C's for
For this equation here, for solving for Q, that wasn't canceling anything. I just made a separate equation there. So I didn't make that very clear, but I basically was thinking about what I needed to do to find out one of the unknowns. And so as I was processing, I was like, okay, well, we don't know CM, we don't know QM. Here we have QM, actually we should be able to derive just from the problem itself. And so that was just a standalone equation I put there because I needed it. It was a good question.
Is that Q is flow, right?
Yeah, Q is flow rate. And that's going to be throughout our classroom. Q is going to be the flow rate. And that'll be volume per time. Any other questions, issues? All right, so I'm not going to start doing the weekly quiz things until the roster is settled, the drop date is ended, so we can all relax about that for another couple of lectures. I'll definitely announce it in class when I put one up, and I'll give you the week, and then I'll figure out the exact dates, but I'll basically give you pretty much 2 lectures and then make sure that you complete that before the next lecture, just to see that you're keeping up with stuff, give you a little bit of feedback about different concepts that I think are important, maybe not something that I want to test you on directly. You know, if we'll have a reading on a couple of case studies, things like that. Yes, I will. And to answer a question online here, I will always post the slides to Moodle, and I'll post them with the annotations for you, so you have that. I'm going to post the video links here. Actually didn't take me too long last time, and if you wanted it sooner or in a different format, you can get it from the Twitch page as well. All right, so if there's nothing else, I'll see you guys on Thursday.